In this section of chapter 6, I would like to discuss about stereochemistry, chiral center, enantiomers, and I'm going to define you and also give you examples, and then you'll also see video clip. And I strongly encourage you, in order to understand this particular chapter materials, that you need to have a model, chemical model. Here I'm defining what is called enantiomer. These are non-superimposable mirror images of each other. If you think about this left-hand side molecule and the right-hand side molecule, COOH on the left-hand side is reflected to COOH on the right side. Hydrogen is reflected to hydrogen through that mirror. Methyl group CH3 is reflected from left to the right. OH is reflected from also one side to the other. Now, so these are mirror images of each other, and they are not superimposable. In order to, as I said, understand it, you make the model and then you find out for yourself. And I'm going to show you by building a model that how I understand that whether they're superimposable or not. Here I made a model of carbon with 4 different groups bonded. So each center represents a chiral center, and I made its mirror image. Now if you can assume that there is a mirror in between these two molecules, then red would be reflected to red, white would be reflected to white, green would be reflected to green, and so that's how you get the mirror images. Now the question is, since these are mirror images, can we superimpose them? If they are superimposable, then they're identical molecules. Let's try that. I'm bringing these two red are together, two green are together, but if you look at the other two atoms, they are not together. So it's pretty much our right hand and left hand. You cannot superimpose them, and they distinctly represent two different hands. So in earlier books, scientists did consider one of them as right-handed molecule, another as left-handed molecule. The another point that I'm trying to make is the way we represent these on a two-dimensional paper is two lines are drawn, and then there is one thick line, which means it's projected towards you. The other one is away from you. You can see it just by looking at one of these models that I have made. If I put a paper, you see that any of those two of those bonds, I hope that you can clearly see it, two of those bonds sit on the plane of the paper, and the red one is projected towards you, and you may not see the fourth one, which is white one, away from you. So when we draw this kind of tetrahedral structures on paper, we draw a thick line to represent a group projected towards you, two solid lines that sits on the plane, and a dashed line which is away from you. In this particular case, it is the white atom. Now let's change these atoms and see whether it makes any difference in mirror image or not. So let's change this red one by a white atom, and white atom could be hydrogen. So that means initially I had 4 different groups. Now I have carbon with 2 groups same. So I consider that those 2 white ones are hydrogen, and the other ones are other atoms. So let's do that on both the molecule, and then I'm going to show you the difference between these two. Okay, now I made this structure with 2 of same atoms around the carbon, and 2 others are different atoms. So those 2 could be hydrogen, and the other 2 could be, say, F and Cl, and the central one is carbon. So I'm bringing the second one close to you. You can see here. Let's try, and these are mirror images. Can you see that? These are mirror images. Green is reflected to green, white is reflected to white. But the question is, are they superimposable or not? Let's try it. They're 100% superimposable. You can see that whites are with whites, green with green, and the purple ones are with purple. So that means even though these are mirror images, they're superimposable to each other, and they're not different molecules. It's the same molecule. So what's the difference here? Well, in this case, two of the groups are the same, and third and fourth are different. On the other hand, the first molecule, all four groups around carbon were different. And that's chiral center. And this is not a chiral center where there are two groups the same and third and fourth are different. So, sometimes it's hard for scientists or anyone to understand whether a mirror image is superimposable or not. So scientists developed a better way of understanding it. So they call it plane of symmetry. The molecule that I built in which mirror image was superimposable, which is, I believe you can see it better now. I can think of a plane of symmetry that cuts this molecule into identical halves. So if I consider this to be plane of symmetry, you can see that I can cut it into identical halves. So each half would have one hydrogen, or white one, on one side. The other hydrogen would be on the other side, and two others are sitting on the plane. So in other words, this is a plane of symmetry. If I had all four different colors, I would never be able to split the molecule into two identical halves. So that's the difference. So what we can tell you now is, rather than examining mirror image, we examine whether that molecule, a particular molecule, has a plane of symmetry or not. Plane of symmetry, existence of plane of symmetry means its mirror image is not going to be a new molecule. It's going to be superimposable. And not having a plane of symmetry means its mirror image is going to be a different molecule. And we call it enantiomer. The equal mixture of enantiomers are called racemic mixture. So from the video clip, we learned that when there is no plane of symmetry, it's a chiral molecule. And what is plane of symmetry? Is the plane that splits a molecule in two identical halves. So keep this in mind. A molecule without plane of symmetry is called chiral molecule. And the central atom is called asymmetric center or stereocenter. So keep this in mind. And molecule with a plane of symmetry is called achiral. There is the A attached in front of that. And if that is the case, mirror image is superimposable and is identical. I already mentioned about this kind of representation. You can see that there is a thick line, that CL is projected towards you. Then two solid lines are sitting on the plane of the paper, and the dashed line or dotted line, that represents the group away from you. So that's the way of representing tetrahedral structure on two-dimensional paper. Now here we're going to do a homework problem, which is problem number 2, page 194. So if you read this question on page 194, the question is, which of the following molecules are chiral? So remember the definition of chirality. Chirality means there should be no plane of symmetry, and when there are four different groups bonded, automatically there'll be no plane of symmetry. So basically we need to look at whether there are four different groups bonded around the central atom or not. Now there are quite a few central atoms in this molecule. Each carbon surrounded by other carbon or hydrogen could be considered to be central atom. But those atoms have 2 or 3 hydrogens, and obviously cannot be a chiral center or chirality center. Okay, you just need to discover one center. Now let's focus on that carbon, but I put the asterisk, and let me identify the 4 groups. This is one group around that carbon, second group around that carbon, third group around that same carbon, and the fourth group around this carbon. Question is, are these groups identical? Answer is no, because the first one is methyl group, the second one is propyl group, hydrogen, and carbon-carbon double bond. So those are 4 different groups, so it has to be a chiral center. So answer is, this represents a chiral center. You just need to discover one chiral center, and that would make the molecule a chiral molecule. So that's the chiral molecule. Now let's try the next one, which is 6.2a, 3-bromopentane. So first write down the structure. Pentane means you must have 5 carbon. So 1, 2, 3, 4, 5. So that's 5 carbon, and it's 3-bromo. So you have a 3-bromo. On the third position you have Br. Now it would be a good idea what could be what you're examining for chirality center or not. We know that these carbons, let me show you with this carbon cannot be a chiral center because you have 3 hydrogens. I've shown you in the video that if I have 2 atoms of the same kind, then it cannot be a chirality center. So you'll have to have 4 different atoms or groups bonded. So none of these carbon could be a chirality center. Same it would be the case with this. But what about this central one? This central one has a hydrogen bonded. So let's circle these different groups bonded. Hydrogen is one group, second group, third group, fourth group. Even though H and Br, they're distinctly different atoms bonded, but there is an ethyl group on each side of that central carbon atom, and they're identical. So it's not chiral. It's not chiral. And it doesn't have a chirality center. In 6.4, we are showing you 3-dimensional structure. And as I already explained to you, the thick line means the group that is projected towards you, and dashed line that's away from you, and solid lines represent on the plane of paper. That means those 2 bonds are on the plane of paper. We just explained to you that a chiral center would have 4 different groups or atoms bonded to around the central atom. So let me show you one of those examples. H, Cl, Br, I. So around the carbon you have 4 different groups. So obviously carbon in this case represents a chirality center. Now its mirror image is obviously going to be a different molecule because they would not be superimposable. Let's draw a better picture at the bottom. So C, H, Cl, and then let's have a thick line, and Br is projected towards you, and I is away from you. Let's assume that there is a plane here in between, and C would be just like before, hydrogen and Cl. Obviously keep in mind C will be reflected the other direction because of the mirror, and I would be going the other way, I, and now Br would be projected towards you. Okay, so these are mirror images of each other. I didn't do a good job in drawing, but hopefully you understand what I tried to draw. Okay, these are non-superimposable, and each center is a chiral center because there are 4 different groups bonded. There is no plane of symmetry. Now, one interesting thing about these molecules, chiral molecules, is they have almost identical physical and chemical properties. but in one property they're distinctly different. What we call rotation of plane of polarized light. One of these isomers, let's call it 1, is going to rotate plane of light to the right hand side, which we call dextro-rotatory, and the other one is going to rotate it to the left by the same amount when they're mirror images of each other. So if it rotates to the left, it's called levorotatory. If it rotates plane of light to the right, it's called dextro-rotatory. So this is the major difference between non-superimposable mirror images. Now here we're showing you the polarized light, how you can get polarized light. Normal light is not a polarized light. That means the light travels at different plane. But when you pass this light, regular light, through certain crystals, you get polarized light. So here you see polarized light. So all these ups and downs you see in the light wave, that they sit on the same plane. Let's assume that that's the plane of the paper that you're looking at. Now when it passes through a sample box, so this is the sample box. So let's write down here sample. Then as it comes out, it rotates either to the right or to the left, depending upon which particular isomer you have allowed to be in the sample box. So one of those isomers would rotate it to the right if it is dextrorotatory. The levorotatory would be the other one, and that would rotate the plane of light to the left. Now here I'm showing you the expression. In many organic chemistry book as well as biochemistry book, you'd often see right after a formula they write down alpha D value. That is nothing but a specific rotation value. How is it defined? Alpha tells us about the angle of rotation. I already mentioned about it, of plane polarized light. L is the sample length of light. That means if I have a bigger sample, obviously I have a larger L value. So it is a sample, and I would have light falling on it. So this is the sample length, L. And C is the concentration of the sample within this cell or box. So it's pretty easy to come up with this number by doing an experiment. And you'd see that these are all listed. Now, in book there is a problem. I think I just wrote down this 6.7, page 196. It's pretty simple and straightforward. Make sure that you have the right unit when you do one such sample problem to figure out how to determine a specific rotation of a molecule.